All right, so today we're taking a deep dive into the world of semiconductors.
Oh, cool.
Yeah, you sent in a chapter from a physics textbook.
Okay.
It's called left206.pdf.
Sounds interesting.
And yeah, so we're going to unlock those secrets of what makes all our electronics tick.
Mm-hmm.
I've got to admit, I use electronics all the time, every single day.
Yeah.
But I have absolutely no clue how those tiny little chips actually work.
Right.
It's like magic to me.
Yeah, well, get ready to demystify the magic a little bit today.
Okay.
It's so fascinating how we rely on semiconductors for basically everything these days. But
Yeah.
most people, they never really stop to think about how they actually work.
Right.
The source material that you sent in, it actually starts by comparing these modern marvels to their predecessors.
Yeah.
Vacuum tubes.
Oh, yeah, like those giant tubes you see in old radios and amplifiers.
Likely.
I did notice that the chapter mentions old TVs used cathode ray tubes, too. And it says that those were also a type of vacuum tube.
Right. They were huge,
Yeah.
bulky, and they've been replaced by much sleeker, more efficient technology.
Makes sense.
What's really interesting is that the left206.pdf actually highlights
Yeah.
what an improvement semiconductors really are.
Okay.
They're so tiny, they use way less power,
Right.
and they just last a lot longer.
So it's fair to say that moving to semiconductors completely changed the electronics industry.
Oh, absolutely. Imagine trying to build a smartphone
Yeah.
with vacuum tubes. Just impossible.
Yeah, that makes sense.
And what's really cool is that our journey with semiconductors,
Oh,
it's far from over.
really?
Yeah. The source material even mentions some really futuristic fields,
Okay.
like polymer electronics and molecular electronics that are still being developed. So,
Wow. So even understanding just the basics of semiconductors could give us a glimpse into the future.
absolutely, yeah.
That's really cool. Okay.
Hmm.
So the chapter starts off by classifying materials based on how well they conduct electricity. Talking about metals, insulators, and of course, semiconductors.
Right.
Could you break those down for us a little bit?
Sure. So think of metals like copper wires.
Okay.
They're basically superhighways for those electrons, allowing electricity to flow through them really easily.
Okay, so that's why we use copper wiring for electricity.
Exactly.
What about insulators? Are they like roadblocks for the electricity?
Yeah, they're like roadblocks. Insulators, they have extremely high resistance, making it nearly impossible for electricity to flow through.
Okay.
Think of things like rubber or glass.
Right.
They're great for insulating wires and preventing shocks.
Yeah, that makes sense.
Mm.
So where do semiconductors fit into all of this?
Semiconductors are kind of the in-betweeners. They fall somewhere between those two extremes.
Okay.
And their resistance, it's not as low as a metals,
Right.
but it's not as high as an insulator's either.
Okay.
But here's the key. Their conductivity can actually be controlled.
Oh, really?
Yeah, under specific conditions, which makes them perfect for building all those electronic components that need to switch on and off or amplify signals.
Oh, okay. That makes a lot of sense.
Mm-hmm.
Speaking of control, the chapter mentions these things called energy bands.
Right.
It says they're ranges of energy levels that electrons can occupy within a material.
Yes.
I'm having a hard time picturing how that actually relates to if something is a metal, insulator, or semiconductor.
Okay, well, let's use an analogy to make it a little easier to understand.
Okay.
Imagine these energy bands as like floors in a building,
Okay.
with each floor representing a different energy level.
Gotcha.
So in a metal, the highest floor, where the electrons hang out, that's called the conduction band.
Okay.
And it's only partially filled.
Okay.
So the electrons can easily move around on this floor, kind of like people walking freely in a room,
Okay.
which explains why metals are such good conductors.
All right. That makes sense. Yeah.
Now, in an insulator, there's a huge gap
Oh.
between the floor where most of the electrons are. That's the valence band,
Mm-hmm.
and that conduction band above it.
Right.
So it took a massive amount of energy for electrons to jump that gap.
Gotcha.
It's like trying to leap over a skyscraper.
Oh, okay.
So the electrons are basically stuck downstairs,
Right.
and electricity can't really flow because they can't reach that conduction floor.
So what about semiconductors then? Do they have some kind of secret staircase?
Well, they do have something special. Semiconductors, they have a much smaller gap
Okay.
between that valence band and the conduction band.
Oh, okay.
More like jumping over a fence than a skyscraper.
Okay.
And it's doable with a little push,
Okay.
like from heat or light or applying a voltage.
So we can control their conductivity.
Exactly, by giving those electrons just enough of a boost to make the jump.
That's pretty clever.
Mm-hmm.
So the left206.pdf chapter goes on to talk about intrinsic and extrinsic semiconductors.
Right.
Intrinsic ones are the pure materials like silicon or germanium.
Yeah.
But then it gets into extrinsic semiconductors, which are doped with impurities, and that increases their conductivity.
Right.
It sounds a little counterintuitive, adding impurities to make something more conductive.
Yeah, it
How
does.
does that work?
So it's all about manipulating that atomic structure.
Okay.
When we dope a semiconductor, we're adding just tiny amounts of impurities to the semiconductor lattice.
Okay.
Just a few atoms per million.
Wow, so that tiny difference at the atomic level makes a big difference in how well it conducts electricity.
It does. It's really about fine-tuning a semiconductor's personality
Oh, okay.
to make it ideal for specific tasks in the circuit.
Gotcha.
So if the impurity has an extra electron,
Yeah.
it's like donating a free electron to the material,
Okay.
creating what we call N-type doping.
Okay.
If it's missing an electron,
Right.
it creates a hole,
Mm-hmm.
which acts like a positive charge carrier.
Okay.
That's P-type doping.
So we're basically increasing the number of those charge carriers to make it more conductive.
Exactly.
I'm starting to see how this relates back to the energy band model we were talking about. So the chapter mentions how doping introduces new energy levels within the band gap,
Yeah.
making it easier for those electrons to jump up to the conduction band.
Right. And that's crucial because in doped semiconductors,
Yeah.
that energy needed to free up those charge carriers, the ionization energy,
Okay.
it's much lower, especially at room temperature,
Oh, okay.
which means we can get significant conduction without needing any extreme conditions,
Gotcha.
which is what makes them so practical for everyday electronics.
All right, so let's break down N-type and P-type semiconductors a bit further, using the chapter as our guide.
Okay.
So for N-type, we're adding pentavalent impurities, meaning they have 5 valence electrons,
Yes.
like arsenic, right?
Right. Those pentavalent impurities donate that extra electron
Yeah.
to the semiconductor lattice.
Okay.
So you end up with a bunch of negative charge carriers.
Okay.
All those free electrons
Yeah,
ready
yeah.
to conduct electricity.
And for P-type semiconductors, we're using trivalent impurities like boron, which only have 3 valence electrons.
Exactly. And when those trivalent impurities fit into the lattice,
Yeah.
they're missing an electron to complete the bonding.
Right.
So they kind of borrow one from a neighboring atom,
Okay.
creating a hole where that electron used to be.
Right.
And that hole can move around,
Okay.
acting like a positive charge carrier.
Yeah.
Fascinating. So in N-type, we're adding electrons, and in P-type, we're creating these holes that act like positive charges.
Yeah.
And this difference is what gives each type of semiconductor its unique properties.
Precisely.
But what happens when you combine the two types?
Ah.
The left206.pdf chapter really piqued my interest with this concept of a p-n junction.
The p-n junction is where the real magic begins.
Okay.
It's formed when you join a p-type and an n-type semiconductor together.
And the chapter mentions these processes of diffusion and drift happening at the junction.
Yeah, it's like a microscopic dance of charges.
Oh, at first, you have all these extra electrons on the N side
Right.
and extra holes on the P side.
Okay.
And they're all eager to even things out.
Yeah.
So they start to diffuse,
Yeah.
moving from areas of high concentration to areas of low concentration.
Mm-hmm.
So electrons from the N side, they wander over to the P side,
Okay.
and holes from the P side wander over to the N side.
So they don't just completely mix together. Something stops them.
You got it. As they diffuse, they leave behind these immobile ion cores,
Okay.
positive cores where the electrons left on the N side,
Mm-hmm.
and negative cores where the holes left on the P side.
Gotcha.
And those immobile charges, they create an electric field.
Okay.
And that electric field, it sets up a drift current,
Okay.
which actually opposes that diffusion current.
So it's like a tug of war between the two currents.
Exactly.
So what happens? Does one current win?
It's not really about winning.
Okay.
It's more about balance.
Okay.
So that diffusion current, it keeps pushing those charges across the junction, while the drift current pulls them back.
Okay.
So this creates a region near the junction
Mm-hmm.
where there are very few free charge carriers,
Okay.
called the depletion region.
So it's depleted of those free electrons and holes that were initially there?
Exactly.
Okay.
And because of that charge imbalance from the positive and negative ion cores,
Yeah.
there's this built-in potential difference across the junction
Okay.
called the barrier potential.
Right.
It's like a tiny wall that prevents further diffusion of charge carriers.
Okay, so the PN junction is in this kind of standoff
Yeah.
with the diffusion and drift currents balancing each other out,
Mm-hmm.
creating the depletion region and that barrier potential.
Exactly.
And all of this is the basis for diodes and transistors and all those other amazing semiconductor devices.
Yeah, the PN junction is the heart of so many electronic components.
This is where it gets really interesting.
Yeah.
The chapter then gets into how applying an external voltage or bias
Mm-hmm.
across the PN junction can dramatically change its behavior. It can, yeah.
It's like we can actually control the flow of current through the diode
Yes.
by making it easier or harder for that current to flow.
Precisely.
That's really cool.
It is, and that's how diodes work,
Okay,
allowing current to flow only one direction.
gotcha. And the LEF 206.pdf source material mentions two types of bias,
Right.
forward and reverse.
Mm-hmm.
Okay, I'd love to unpack those, but maybe we should save that
Yeah, that's a good idea.
for part 2 of our semiconductor deep dive.
Okay.
I'm already feeling like I'm starting to understand this hidden world of electronics a little bit.
It's amazing, isn't it?
It is, yeah. What do you think?
I agree. It's incredible how something so tiny can have such a huge impact on our lives.
Mm.
And we're just getting started.
Oh, wow. Okay, well, stay tuned because things are about to get even more interesting in part 2.
Definitely. Welcome back to our semiconductor deep dive.
It's really amazing how much these tiny components impact our lives, isn't it?
It is.
And we left off talking about PN junctions.
And this idea of applying a voltage or bias to control that current flow.
Yeah.
So the left206.pdf chapter dives into forward and reverse bias.
Right.
And I'm really curious to learn how they work.
Okay, so let's start with forward bias.
Okay.
Imagine you've got a battery connected to your PN junction.
All right.
In forward bias, you connect the positive terminal of the battery to the P side
Okay.
and the negative terminal to the N side.
Gotcha.
So it's kind of like you're encouraging the charge carriers to mingle.
So instead of pulling them apart like in the depletion region, you're kind of nudging them closer together.
Exactly. This reduces the barrier height.
Okay.
It shrinks the depletion region
Mm-hmm.
and allows current to flow more easily.
Okay. That makes sense.
It's like opening a gate to let the current flood through.
But wouldn't that mean a huge amount of current would flow
Yeah.
and potentially overwhelm the circuit?
That's a great question.
Yeah.
While current flows more readily in forward bias, the amount is still controlled
Mhm.
by factors like the applied voltage
Right.
and the characteristics of the diode.
Okay, so it's not a complete short circuit.
Right. It's like a controlled flow, not a complete free-for-all.
Got it. Okay, what about reverse bias then? What happens there?
Okay, so in reverse bias, you flip those battery connections.
Okay.
So the negative terminal is connected to the P side
Mm-hmm.
and the positive terminal to the N side.
Okay.
So it's like telling the charge carriers to stay on their own side of the junction.
So instead of encouraging them to mingle, you're kind of reinforcing that wall at the junction.
You got it. This widens the depletion region,
Okay.
increases the barrier height,
Mm-hmm.
and makes it practically impossible for current to flow.
Right.
Think of it like trying to push a boulder uphill. It's just not going to happen easily.
So forward bias is like opening the gate,
Right.
and reverse bias is like building a bigger wall.
Exactly.
Okay, that helps me visualize it.
Okay.
And this one-way flow of current in a diode is what makes them so useful.
Yeah.
For things like converting AC to DC.
Exactly. That's the basis of rectification.
Okay, let's break down rectification a little bit.
Okay.
So I know most electronic devices need DC power,
Mm-hmm.
but our standard wall outlets provide AC power.
Right.
So rectification is that process of converting AC, which constantly changes direction,
Right.
into DC, which flows in only one
You
direction.
nailed it. And diodes, with their unique one-way current flow,
Yeah.
are perfect for the job.
Okay.
They block the negative half cycles of the AC waveform,
Okay.
allowing only the positive half cycles to pass through.
So it's like they're chopping up the AC wave, letting only the positive parts through to create a pulsating DC output.
Exactly.
Okay.
Hmm.
It's amazing how such a simple concept can be so fundamental to making modern electronics work.
Yeah.
But I'm curious, is there anything else involved in getting a smooth and stable DC output?
Great question.
Yeah.
So the left206.pdf actually also mentions using capacitors
Okay.
in conjunction with diodes for filtering. And that helps smooth out those pulsating DC bumps to achieve a more stable voltage.
So it's like refining the process, going from a rough cut of DC to a nice, polished, finished product.
Exactly.
Fascinating. Earlier we touched upon that exciting world of future semiconductor technologies,
Right.
like polymer electronics and molecular electronics.
Yes.
The chapter mentions those briefly, but I'm really itching to learn more.
Yeah, those fields hold so much promise.
Okay.
Just imagine flexible electronics,
Oh, wow.
molded to any shape, or wearable devices,
Yeah.
so seamlessly integrated they feel like a part of you.
Yeah.
We could even see biocompatible electronics
Oh, wow.
interacting directly with living tissues.
That sounds like science fiction,
It does.
but it's based on those same fundamental principles of semiconductors that we're talking about today.
Exactly. And this is where things get really interesting.
Okay.
These new materials, like organic molecules or polymers,
Hmm.
they could overcome some of the limitations of traditional semiconductors.
So it's not just about miniaturization anymore.
No.
It's about exploring new possibilities for how we design and use electronics.
Exactly. For example, polymers.
Yeah.
They can be flexible,
Right.
lightweight, and even transparent,
Oh, wow.
opening up all these design possibilities
Yeah.
that are just impossible with traditional silicon-based electronics.
That's incredible, but I imagine there must be some challenges in working with these new materials.
Oh, of course.
Yeah.
It's not all smooth sailing.
Right.
One of the main challenges is achieving that same level of performance
Okay.
and reliability that we've come to expect
Mm-hmm.
from traditional semiconductors.
Makes sense.
These new materials, they often have lower conductivity
Right.
and can be more sensitive to environmental factors.
So it's like a trade-off,
Right.
gaining new capabilities, but needing to overcome new hurdles.
Exactly.
Right.
But researchers are making significant strides in developing these technologies.
Yeah.
For instance, they're exploring new molecular structures
Right.
and fabrication techniques to improve that conductivity and stability.
That's exciting.
It is.
So even though these technologies are still emerging, they really do have the potential to revolutionize electronics in the future.
Without a doubt.
Yeah.
Imagine a world where electronics are seamlessly integrated into our clothing,
Yeah.
our bodies,
Right.
and even our surroundings.
Wow.
It's a future that's closer than we might think.
That's really cool. Okay, so we've covered forward and reverse bias, explored rectification,
Right.
and even glimpsed into the future of semiconductors a little bit.
Yeah.
But the Left 206.pdf chapter also mentions this concept of breakdown voltage.
Oh, that's a good point.
Yeah.
It is important to understand the limits of those PM junctions.
Okay.
So normally, a reverse bias diode,
Yeah.
it blocks current.
Right.
But if that reverse voltage gets too high,
Okay.
it can overwhelm the barrier potential,
Right.
causing this surge of current.
So it's like the wall at the junction finally crumbles under pressure.
Yeah. Exactly. And there are two main types of breakdown: Zener breakdown
Okay.
and avalanche breakdown.
Those sound intense.
They do.
Okay, what's the difference?
So Zener breakdown happens at lower voltages,
Okay.
and it's caused by this quantum phenomenon called tunneling.
Oh,
Basically, electrons can tunnel through that barrier potential,
right.
even if they don't have enough energy to overcome it in the classical sense.
Oh, okay.
It's like they're finding a secret passage through the wall.
Quantum mechanics is so mind-boggling.
I know, it's pretty wild.
Okay, and what about avalanche breakdown?
Okay, so avalanche breakdown, this occurs at higher voltages.
Okay.
And here, that electric field in the depletion region gets so strong
Yeah.
that it accelerates the few free charge carriers that are present to super high speeds.
Okay.
And as they collide with other atoms, they knock loose even more electrons,
Right.
creating this cascade effect like an avalanche,
Oh, okay.
leading to a really rapid increase in current.
So both Zener and avalanche breakdown, they both involve this sudden increase in current,
Yes,
but they happen for different reasons and at different voltage levels.
exactly.
Okay. And while breakdown can be damaging if that current isn't limited,
Right.
it's not always a bad thing.
It's not, no.
So the Left 206.pdf source actually mentions how Zener diodes are used for voltage regulation.
Right.
Now, that's fascinating. So you're telling me we can harness this potentially destructive phenomenon for something useful?
We can.
How does that work?
So Zener diodes are specially designed to operate in the breakdown region.
Yeah.
They have a very precisely controlled breakdown voltage,
Mm-hmm.
which means they can maintain a constant voltage
Okay.
across their terminals, even if the current through them varies.
So it's like a safety valve for voltage,
Yeah.
keeping it steady even when things get a little wild in the circuit.
Exactly. They're used in all sorts of applications.
Okay.
From power supplies to surge protectors,
Yeah.
making sure those sensitive electronic components get a stable voltage.
Wow, that's amazing. So we've gone from these basic building blocks of semiconductors
Right.
to the incredible complexity of PN junctions and breakdown.
Yes.
But now I'm curious about how all of this comes together to create those tiny, powerful devices we use every day.
Mm.
Things like transistors.
Transistors, they're truly remarkable.
Yeah.
They're the workhorses of modern electronics.
Right.
Tiny switches, amplifiers
Right.
that make everything from smartphones to supercomputers possible.
And they build on that PN junction concept, but with a little twist, right?
You got it. So while a diode has a single PN junction,
Yeah.
a transistor has two PN junctions connected back to back.
Okay.
And there are two main types.
Right.
Bipolar junction transistors,
Okay.
or BJTs,
Gotcha.
and field effect transistors, or FETs.
Okay, let's start with BJTs.
Okay.
So the left206.pdf source describes them as having 3 layers of semiconductor material,
Right.
either NPN or PNP configurations.
Exactly. Those 3 layers form 2 PN junctions in a row.
Yeah.
Each layer has a terminal,
Okay.
the emitter, the base, and the collector.
Okay, so I remember reading that a small current injected into the base
Yeah.
can control a much larger current flowing between the emitter and the collector.
Right.
Is that how they amplify signals?
Exactly. It's like using a small lever to move a much heavier object.
Okay.
And that amplification ability is what makes transistors so powerful.
Right.
For instance, they can amplify those tiny signals from a microphone
Yeah,
to produce the sound we hear through speakers.
that makes sense. And they can also act as electronic switches,
Yes.
rapidly turning current on and off.
Right.
That's what makes digital electronics possible, right?
Absolutely. In digital electronics, information is represented as a series of ones and zeros,
Right.
corresponding to the on and off states of those transistors.
Gotcha.
And it's incredible to think that everything our computers and smartphones do
Yeah.
boils down to these simple switches flipping billions of times per second.
It's mind-boggling. And that miniaturization of transistors over the years has been incredible.
It has.
You know, going from those bulky vacuum tubes to microscopic transistors
Right.
packed by the billions onto integrated circuits.
It's like shrinking entire electronic systems
Yeah,
down to the size of a fingernail.
that's wild.
And the left206.pdf doesn't stop there. It also introduces field effect transistors, or FETs.
Okay, I'm all ears. How are FETs different from BJTs?
Okay, so instead of using a base current
Okay,
to control the flow of charge carriers,
right.
FETs use an electric field
Okay,
applied to a gate terminal
okay.
to modulate the conductivity of a channel
Right.
between the source and drain terminals.
So it's like opening and closing a gate to control the flow of water in a channel?
Exactly. And because FETs have very high input impedance,
Okay,
they draw very little current at the gate,
okay.
making them incredibly efficient
Right.
and sensitive.
Gotcha. The chapter mentions that FETs are the dominant type of transistor in modern integrated circuits.
They're incredibly versatile,
Yeah.
and they can be miniaturized to an amazing degree,
Right.
which is why they're perfect for packing billions onto a single chip.
It's truly remarkable what we've been able to achieve with semiconductor technology.
It is.
This deep dive has been incredible.
Yeah.
But we are running out of time.
Oh, we are.
Yeah. Should
Yeah.
we continue this fascinating discussion in part 3?
I agree. There's still so much more to explore in this microscopic world.
Right.
I mean, we haven't even touched on the concepts of capacitance,
Yeah.
the dynamic behavior of p-n junctions.
Okay, well, let's continue this journey in part 3.
Sounds good.
Welcome back to the final part of our semiconductor deep dive. It's been quite a journey so far.
It has.
We've explored the fundamentals, delved into the magic of PN junctions,
Right.
and even touched upon the future of electronics.
Mm-hmm.
But the left206.pdf chapter, it doesn't stop there.
It doesn't.
It takes us even deeper into those PN junctions.
Wow. It's like zooming in from a satellite view all the way to street level,
Okay.
revealing all those fascinating details.
I like that analogy. Okay, so
Yeah.
we've talked about how these junctions behave under static conditions,
Right.
but they've got this whole other layer of complexity when things start changing rapidly.
Yes.
Okay, I'm intrigued. So what kind of dynamic behavior are we talking about here?
Well, remember how the width of the depletion region
Yeah?
changes as the voltage across the junction varies?
Mhm.
That change in width, it actually affects the capacitance of the junction.
Okay.
It's like having a tiny capacitor
Mm-hmm.
that can change its value super fast.
I'm having a little trouble picturing that. How does the width of that depletion region relate to capacitance?
Okay, so think of a capacitor as two plates separated by an insulator.
Okay.
The wider the separation between those plates, the lower the capacitance.
Okay.
In a p-n junction, that depletion region acts like the insulator between those two plates,
Right.
formed by the p-type and n-type regions.
So when that depletion region widens, it's like increasing the distance between those capacitor plates, which lowers the capacitance.
Exactly.
And when it shrinks, the capacitance goes up.
Right.
That's pretty cool, but why does this matter so much for these semiconductor devices?
Well, it matters a lot, especially when those devices are operating at high frequencies.
Okay.
These capacitance effects, they can influence how quickly the junction can respond to changes in voltage,
Right.
which impacts the performance of things like transistors and integrated circuits.
Gotcha. And the LEF 206.pdf chapter breaks down these capacitance effects into two types:
Yes.
diffusion capacitance and depletion capacitance. So what's the difference?
Okay, so diffusion capacitance is related to the storage of minority charge carriers
Okay.
in the neutral regions near the junction.
Right.
Remember how we talked about those free electrons in the N-type material
Yeah.
and those holes in the P-type material?
Right.
Well, in a PN junction, there are also a few minority carriers
Okay.
hanging out on each side.
Gotcha.
So electrons on the P side and holes on the N side.
So they're like visitors in a foreign land.
Exactly. And when the voltage across that junction changes,
Okay.
those minority carriers, they need some time to adjust and move around.
Right.
And that movement and storage of minority carriers,
Yeah.
that contributes to diffusion capacitance.
So diffusion capacitance is kind of like a delay caused by those minority carriers needing to adjust.
Exactly.
Okay, I think I'm starting to get it.
Okay.
What about depletion capacitance then?
Okay, so depletion capacitance, that's tied directly to the change in the width of the depletion region itself.
Okay, so that wall at the junction.
Yes, that wall.
Okay.
And the size of that wall, it can change
Yeah.
depending on the applied voltage.
So if the voltage increases in reverse bias, that wall gets bigger,
Yes.
which means the depletion capacitance decreases.
Right.
And if the voltage decreases, the wall shrinks. Capacitance increases.
Exactly.
Okay, got it.
And this depletion capacitance is especially important in reverse bias junctions
Okay.
because that depletion region, it can be quite wide,
Yeah.
leading to a pretty significant capacitance effect.
So these capacitance effects add a whole other layer of complexity
They do.
that engineers have to consider when they're designing these devices.
Absolutely.
It's amazing how much depth there is to this topic.
It is. It's a testament to human ingenuity
Yeah.
and our understanding of the physical world.
Right.
Think about it.
Yeah.
We've gone from the basic structure of atoms
Right.
to the complex behavior of PN junctions.
Mm-hmm.
And now we're even talking about the dynamics of capacitance at the microscopic level.
And it all started with those early pioneers experimenting with materials like galena,
Right.
as the LEF 206.pdf chapter mentions.
Right.
They were working without a full understanding of the underlying physics, which is incredible.
They were true trailblazers. Their work paved the way for the transistor,
Right.
which totally revolutionized electronics.
Yeah, in the mid-20th century. And the pace of innovation since then has been astounding.
It has.
The chapter highlights that incredible miniaturization of transistors
Right.
over the decades,
Yeah.
leading to the integrated circuits that power all our modern devices.
And it's an exponential growth
Yeah.
driven by breakthroughs in materials science, lithography, and all those fabrication processes.
Right.
We've gone from a handful of transistors on a circuit board
Yeah.
to billions on a single chip,
It's crazy.
all in just a few decades.
It really boggles the mind to think about how much computing power we have today compared to just a generation ago.
Yeah, it's amazing.
But what's even more amazing is this trend shows no signs of slowing down.
It doesn't. Researchers are continually pushing those boundaries of miniaturization,
Right.
investigating new materials, and exploring novel architectures to develop even more powerful and efficient electronics.
The LEF 206.pdf chapter even mentions the possibility of molecular transistors,
Oh, yeah.
where single molecules act as electronic switches.
That's right. That sounds like science fiction.
It does.
Harnessing the power of individual molecules for
Wow.
computation.
Wow.
It's incredible to think that could be a reality one day.
It's really a testament to that power of scientific understanding.
It is.
By delving into those fundamental laws of nature, we can
yeah.
unlock all these possibilities
Yeah,
and create technologies that we once considered pure fantasy.
absolutely. And Who knows what the future holds?
Yeah.
Maybe one day we'll have deep dives into quantum computing
Right.
or biointegrated electronics.
That's a really exciting thought. This deep dive into semiconductors has been incredible.
Yeah.
It's given me a newfound appreciation for all the ingenuity and effort that has gone into developing this technology.
It's pretty remarkable.
It really is, and it's also sparked this sense of wonder
Yeah.
about the endless possibilities that are ahead.
Definitely.
That's been quite a journey.
It has been a fascinating exploration, hasn't it?
It really has.
And it highlights the power of curiosity and the importance of always continuing to learn.
Right.
Who knows? Maybe you, our listener, will be the one making those groundbreaking discoveries in the future.
That's a great note to end on. Thanks for joining us on this deep dive into the fascinating world of semiconductors.
Of course.
We hope you enjoyed it and learned something new along the way.
I hope so too.
Until next time, keep those brains buzzing.